Okay, thank you, Bill. I appreciate being invited. I wanted to start out with some just introductory material about the canal. I think most everyone from this neck of the woods knows a lot about it, but just as a review, it was one of a very amazing engineering achievement. It did a lot for New York State, for the country, especially New York City, and of course, the communities along the canal probably wouldn't be here if it hadn't been for the Erie Canal. It was built between 1817 and 1825. I think it cost about $7 million. The point is often made that the quote unquote engineers who designed it really as they went along were actually lawyers. At least Benjamin Wright, the head man, was a lawyer, and it wasn't that unusual. He had good surveying skills, which lawyers who did real estate work at that time generally were good surveyors. So surveying, of course, was a very critical part of designing, but also guiding the construction of the canal across the state. The canal was 363 miles long, connected Buffalo with Albany. You can see Syracuse there, almost in the middle. It was the original canal was built 40 feet wide and 4 feet deep, of water, and it was a huge success from the very beginning. The tolls that were collected paid the investors handsomely, and they had money to spend. They knew that it should be enlarged, and in 1835 they started to do that. So when I'm talking about the water supply, keep in mind that they had made a lot of money. The Canal Corporation had made a lot of money, and they knew that they could get more traffic if they enlarged the canal, which in 1835 they started to do that. And I think that enlargement period ended around 1860. The enlargement meant that the size went the dimensions went from, from 40 by 4 feet deep to 70 feet wide by 7 feet deep of water. And they doubled the locks at that time. So instead of a single lock, locks were put side by side in almost all locations. And as I said, it benefited many towns and cities, and especially New York City owes a lot to the Erie Canal. The people often ask me, how did they get the barges? How did the barges get down the Hudson? They put them in rafts or tows and pulled them or pushed them down to the city with steamboats. This is a painting by a man, George Harvey. I think this painting is owned by the University of Rochester. It was painted in 1837. That was what attracted me to it. It shows one of the early boats, the passenger boat, called a packet. Packets were the only way you could travel you could get a ride on a cargo type boat, a barge or cargo boat. But in a packet, you could sleep, eat, relax on deck. It must have been an interesting experience. The mules or the horses were kept in a stable in the stern section. You ate, they slept, one on top in bunks, 3 high. You kind of wonder what it smelled like. No wonder they went out on the deck, as you see here in the picture. The packets traveled at about 5 miles an hour, and the other cargo boats traveled at about 2 miles an hour. So the packet was a little bit faster, but of course the packets disappeared in the mid 1800s as the trains just made travel more convenient. So the packets were fine while they lasted, but the trains were a better mode of transportation, more convenient. As my title indicates, the canal had a water problem. You don't read a lot about that in material about how the canal was built and used and so on. But whenever there was a dry period, a drought, there would often be, how do I move your picture, Bill? Your picture's in the way here. Ah, there it is. There were dry periods, especially in the summit section, and I'll explain what the summit section is here in a second. This was a costly problem. You'll see when there's not enough water, it's harder to pull the boats. You can't carry as high a load on the cargo boats. And of course, they had the money to spend after 1835 in the expansion. So the engineers were looking for all kinds of water from all sorts of sources. And just as an intro to what I'm going to be saying, new sources meant adding feeder canals wherever they could, diversion dams that were needed with the feeders. And then when they still weren't getting enough water, I'm going to show that they built dams and reservoirs. Many of them, I'm sure you're familiar with. And they also, many people don't realize, they snatched water, diverted water from neighboring watersheds, which creates problems in some cases. And I'm going to describe briefly one of those problem areas on the Black River up in the Adirondacks. So as I started to say earlier, the water problem was greatest in the summit. Here's the summit section. In the very, very beginning, some people thought that they could they had a very good source of water at Lake Erie. They could use that water all the way down to Albany. And of course, that you would have to have a much longer canal because the canal would have to move south toward higher ground all the way along. And you would lose water, of course, as it flowed across the state, and the amount of water that you would have to have flowing up here to meet the needs of leakage and so on down, and to make the locks work and so forth. That would be so huge, it would be like a water slide at a water park, I suppose. There would have been just too much current up here for it to be usable. So that was impractical, but Lake Erie took care of the western parts of the canal very well. And then in the middle here, of course, what do we have? The Finger Lakes. And the Finger Lakes they put dams on many of the, I think all of the Finger Lakes eventually, and would release water during dry periods, and water problems weren't that great over in this part of the canal. But here in the summit section, there were problems, and I'll explain a little bit about that. On downstream here, of course, going from Utica, the eastern side of the summit, on down all these locks, they were able to make do with the water that, of course, was flowing in that direction from the summit, and a few sources along the way. Here's a rough map of watersheds, rivers in the New York State, and you can see the summit section is here. A little bit of it in Onondaga County, most of it in Madison. It extends from, it's north of the Shenango River here, and the Mohawk is, of course, at the eastern side. So this part of the summit is in the Great Lakes watershed, from like here over, and this part to the east is in the Hudson River watershed. So that's part of the problem, with shortages of water. Here's a slide describing how water was lost from the summit. The The first down here in the lower right shows a lock, a typical lock. And to make a lock work, you have to have it, you have to, boat coming up, you put the boat in, let the water from above fill the lock up, the boat rises, you open up the doors, and the boat moves out into the upper pond. And then when boat goes down, water is released and goes into the lower pond. So in the summit section, you had water being used in this way in the east and in the west. And that, of course, put pressure on the, that part of the canal. You also had these losses, and this was the important one. I'll show you in a minute. Seepage, especially through the, the man-made, the fill berm where the towpath was located. You've had a little bit of loss to evaporation, and there were often plants growing along the edges, and you had, evaporation from the leaves of plants, evapotranspiration. So that was, part of the loss. And the total, let's just talk about the total that you can see. Seepage was up here, seepage was the greatest flow rate. Evaporation, not so much. Lockage, lockage would be at maximum when locks were being filled and emptied, say every 20 minutes or so, every hour of the day, which of course would be rather unusual. But so that represents a maximum loss through lockage. So we end up with about, for the summit section, about 200 cubic feet per second. Just for comparison, let's see, City of Syracuse uses about 70 cubic feet per second of water for its drinking water supply from Skaneateles Lake. Limestone Creek down here below my house is about, I don't know, average through the year is about 150 cubic feet per second. So we're talking about a flow of water, in that, if that helps you picture water flow, that's what we're talking about. But this is very important, over that 60-mile summit section, that loss of 200 cubic feet per second would be about 8 inches of depth per day. So in the original canal, they only had about half a foot of depth to play with, the clearance below the bottom of a loaded boat. In the enlarged canal, you had about a foot. So it didn't take very long before, you were in trouble. And the troubles were the following. When the clearance between the boat and the bottom became less than, say, 6 inches or 1 foot, then drag increases. The water that you're pushing out of the way has to move underneath the boat, and it increases friction on the bottom of the boat, and it increases the work that the mules, horses, have to use. And this was I asked this mule what he thought. They don't like it. The other problem was that when you had a low water, the boats could not carry a full load. So for example, in the early canal, if you had a 30-ton cargo, you could gain about 6 inches of draft if you reduce that load to, say, about 25, 23 tons. But the owner of the boat didn't earn as much money. And of course, the Canal Corporation didn't make as much from tolls if they had to reduce the load. So when I said it was costly, that's what it cost in terms of loss of tolls and income for the boat owner. There were also long waits and lines at the locks. And I read in, I don't know, one of the good books about Bernstein's, maybe about the Erie Canal, they said there would be long lines of, you'd have to wait at a lock for someone to come down before you could go up. And these long waits, the people working on the boats would run to the nearby tavern and try to get back on the boat later. And you lost maneuverability. And this was important. You didn't want it with 30 tons or with the larger boats in the large canals, like 200 tons. You didn't want to bump anything because you would break something. These were wooden boats, of course, and you couldn't afford to bump another boat or to bump the bottom or the shore. And you didn't want to have your canal boat rest on the bottom because they weren't designed for that at all. You know, they would start to leak and maybe worse. And you didn't want to sink in the canal for sure. So let's just take a couple minutes and talk about how water supplies were connected to the canal. This is a fun area, has been a fun area for me, going across the state, looking at different sites, where they use different methods to connect. This is one I point out here. This is based on the Schoharie Creek crossings. These are connections that are called crossings, meaning the canal had to cross a water body, a stream usually. And over at Schoharie, the stream, of course, is the Schoharie Creek, and the canal is coming from the Utica direction here. And it's about, this water level in here is about 6 feet higher than the water level in the pool. They call it a slack pool behind this low dam. And the low dam brings the water level up so that this water in the creek then tends to flow past the guard gate and then on down through the canal to Albany. So that's how water got into the canal. The supply supplied the canal at the Schoharie Creek crossing. And there were many others similar to this, although I think the Schoharie Creek one was one of the more difficult crossings along the whole canal system. Initially, this is very interesting. Initially, they took the mules here and put them on a ferry boat and took them across. And then they pulled the boat across with a rope. And then they built a bridge here. And the mules went across on the bridge and pulled the boat across and got it headed into the other side of the canal, headed toward Albany. They had so many problems. I don't know, did anyone hear the lunchtime speaker at the Erie Canal Museum the other day? David Brooks, I think his name. He's the person who looks after this historic site at Schoharie. But he said they had so many problems with the dam washing out that they eventually put in a big aqueduct. And then this canal right here became a feeder canal, sending water on downstream where it joined the water that came through the aqueduct. So they got tired of replacing this dam. But after this then just became a feeder system, which I'm going to talk about next year. So this is a stream crossing, just like you might see on a level spot, like at Rome, where the water can go, in and out of this elevation drawing. They put a dam or a weir over here underneath the towpath, a bridge over the towpath. So there were other arrangements that you'll see as if you find any parts of these supply locations. This was the most desirable approach, was the feeder canal connection. And they always tried to many of these crossings that I just showed you were converted to a feeder canal connection, mainly because you could build into the system these gates. You could open and close them to control the water in the feeder canal. So the essence of a feeder canal connection was you had an aqueduct over the stream. And I'm going to show you an example of Limestone Creek. You had an aqueduct over the stream, and then on the hillside leading into the canal, near that aqueduct, usually, not always, you had the feeder canal. And then upstream here, this could be just hundreds of feet, or it could be miles, like the Butternut Creek, the Orville feeder. It's miles before you get to the location of the Diversion Dam. But if you going across the canal, look for aqueducts, there's a feeder canal, or at one time there was a feeder canal and a diversion dam and gates and so forth. Many of those are gone now, but we've got a few still left in the area, as we were talking earlier. Here's a crude plan drawing of the feeder canal. Here's the feeder canal tucked in along the hillside near the stream. Here's where the stream goes down and under the aqueduct, and the gates controlled. When you had a flood in the stream, you could use the gates to protect the main canal. And that was what was very desirable, because with the canal operation, they hated floods. Floods were, very expensive. They were always repairing flood damage, in the late spring. And here's, of course, our good old Limestone Aqueduct on the, the old Erie Canal State Park. This is going over to DeWitt, and this was built probably back when they were turning our part, this part of the Erie Canal into a feeder for the Barge Canal. And so this was built. This channel was built so the water that came from DeWitt, from the Butternut Creek feeder, Orville, they call it the Orville feeder, that was a way for it to get over toward the summit of the Barge Canal near Rome. So that's why this was basically a conduit that made this a part of the feeder system for the Barge Canal. And of course, today we benefit from it because it makes the park better. And of course, these gates are over by Fayetteville by the new bridge. The dam, the state took the dam out, I don't know, 10, 12 years ago, maybe. These gates are not for the canal, but were there to control the water to the old canal when it became a feeder stream for the Barge Canal over by Rome. So this was not for, back I'll show you here an old picture. This is a 1898 Geological Survey map showing here's the aqueduct up here, and you can see where the water reached the aqueduct. The Ledyard Canal dike water came down the hill where it still does and went into the feeder canal here, and then there was a diversion dam right about where the dance studio is today, and that fed water into the feeder, and then the feeder went on down. Today, the old dam and the bridge and so on are, down here someplace. But like I said, that was all put in for as a feeder for the Barge Canal. Oh, that's what I was looking for. Yeah, you can see down here, this is where our little diversion dam would have been, and here's where the Ledyard dike water came in, and the feeder, goes along like this. The aqueduct was here, and that's the Fayetteville Limestone Creek feeder. So they didn't, in most cases, get enough water. They would add a feeder, a feeder canal, diversion dam, and so on, and then they'd have a drought, a dry period, and there would be problems with water depth. And so they would then go to the next stage. Remember, this was a trial and error type process. And they built dams, large reservoirs. And these were never tiny reservoirs. These were hundreds to thousands of millions of, like a billion cubic feet of stored water. These had to be fairly large to be useful at all. This is an old, I wanted you to see what all the original dams were, these stone and log wood crib dams. This is from a picture over on East Canada Creek. So that was the only good log crib dam I could find, a picture. This is after about 1900, wherever they wanted to keep a dam, they they built concrete dams like this one at Old Forge. This is the Old Forge Reservoir here, which is First through Fifth Lakes. They're above Old Forge, if you've ever been in that neck of the woods. That I'll tell you a little bit more about later, is basically a flow regulating reservoir for the mills at Watertown. That's why this was kept and why the log crib dam was replaced and so on. But you know, this is a situation in which this concrete dam, like the ones they kept, almost all of them, the concrete change to concrete occurred around the turn of the century. So how does a flow regulating dam work? It's pretty simple. You in the spring, you fill it up with usually with snow melt, any rain you can catch, runoff from the watershed. Then you take that stored water. You have someone to operate the, operate the facility. All these dams had a dam tender, just like the locks had a lock tender. They had a dam tender that tried to keep the dam from being washed out during storms, but also to be there to release the water when that needed to be done, during the next period, which of course is in the summer. Early fall was typically when you needed to augment the downstream flow. So that is what a flow regulating reservoir is. It's what they do today. And there are many of these around. They're no longer in this area used for supplying water to canals during low flow periods, but they are used for hydroelectric generation. So to get more consistent, more profitable hydroelectricity generation, it's good to store water and release it during low flow periods so you can get the maximum utilization of your turbines. In the spring during high flow, the flow is greater than the capacity of the turbines in many cases. And then in the fall, it would be less than. So you release this water and try to keep the flow in the stream. And so just to give you a little picture of in our local vicinity, the flow regulating dams and reservoirs over here, Onondaga, and then many of them over here in Madison. And all of these are connected to one of those feeder canal streams that I talked about. And usually some of the aqueducts are, almost all of them are connected with an aqueduct on the canal. Here's the good old Summit section, over Syracuse to Janesville Reservoir is, of course, on Butternut Creek, and that's what supplied water to the Orville feeder that we know where that goes in at the end of the park in DeWitt. DeRuyter is the reservoir, flow regulating reservoir for Limestone Creek, and Cazenovia Lake here and Erieville are for Chittenango Creek. And of course, we had a Chittenango feeder. It's mostly all gone now, but there might be a little bit of it left there at the next to the museum. But anyway, that Chittenango Creek, and then all of these over here were left over from the Shenango Canal that went from Utica down to Binghamton. And when the Shenango Canal was decommissioned in the 1870s, they blocked it off here, and all these then fed into the Shenango Canal and went down to the Erie Canal at Utica. So they turned those into flow regulating reservoirs like the others, but used the Shenango Canal to get the water down to the Erie Canal. But you can see the engineers from the Canal Corporation just worked steadily. The feeder canals, they imagined would be a great improvement, and probably were, but then they still had periods of water shortages, and so they built these flow regulating reservoirs. And just to remind you, here's the DeRuyter Reservoir. You can see this little stream down here is very interesting. That's where this stream is connected to the middle branch of the Tiefneoga Creek. And there's a diversion dam on the Tiefneoga Creek. And this is where they they get water from the Susquehanna River Basin and direct it north. And of course, in here, it's now headed toward Limestone Creek. So this is one of those locations where they take water from one watershed and move it into where we can get some useful, they could use it in the canal. DeRuyter is one of those locations. Here's the dam is a earth-filled dam, and it's right down here. Just a couple years ago, the Canal Corporation had to replace the spillway and the pipe that they use for controlling the outflow from the reservoir. This was sort of out of commission for, I think, one or two summers. So they added lots of feeders between the original, when the original canal started in 1866, after they finished the enlargement. There weren't that, they left things pretty much alone, except for as far as water supplies are concerned, except for in this summit section where they had the most problems, as I've been saying. But look at, if you look at the dates, Limestone Creek feeder was built in 1852. And then they probably weren't getting enough flow in the creek during dry periods, and they added the DeRuyter Reservoir. And like the Butternut Creek, the Janesville Reservoir in 1874. So here's how the total reservoir volume increased. It was much of this increase here is from what I'm going to talk about next, the Black River watershed up in the Adirondacks. So I mentioned this, the DeRuyter Reservoir, Susquehanna River water. It was at this location sent to the Great Lakes through Limestone Creek, Susquehanna River over above Utica, the connection to the Shenango Canal that I mentioned, and it sent water in some places to Oriskany Creek, but that was, you could argue, Susquehanna River water to some extent, and it was sent into the Mohawk River watershed. And here's the diversion that caused interesting problems that I'm going to talk a little bit more about, is the Black River, which is in the Great Lakes watershed. And it sent water to the Hudson River watershed. You could also argue that maybe some of that gets back into the Great Lakes, but it is still a conduit of Great Lakes watershed water to the Hudson. The Black River, here's you can see the Susquehanna River water that I said went through the Shenango down was here. The Susquehanna River water at the DeRuyter was here. And then we have the Black River watershed. These are in the Great Lakes. Black River watershed is in the Great Lakes watershed. And of course, the Mohawk River, goes this way. So the Black River became a very important source because it is a wet watershed. Typical total precipitation in New York is 35, 36 inches a year. Up in the Black River, it's 50. And of course, a good part of that is like today, lake effects. Well, lake effects, no, maybe isn't the case today. So how did the water flow from the Black River to the summit section of the canal? There was a low diversion dam and small impoundment at Forestport on Route 20. You cross the big iron bridge at Forestport going up Route 28. That is the pool there you'll see underneath the bridge that feeds into this diversion dam. Then they had this beautiful feeder canal from Forestport over the village of Boonville, and then it flowed down the Black River Canal to Rome. And the Canal Corporation, they were eager to get this water from the Black River for the summit. They weren't all that eager to build the Black River Canal, but the Black River Canal did give them a conduit down to Rome. And so the people in the Black River Valley up there, the farmers, and particularly the sawmill people, wanted to get their lumber to markets in New York City and so on. So they really lobbied for a canal. Here's just a couple of pictures, current pictures. Here's the Diversion Dam over there. You can just barely see it. The truss bridge over Route 28 that most everyone has crossed, I would imagine. Here's the Diversion Dam. Of course, it was a log crib dam in the beginning. Now it's concrete and stone. Here's a beautiful feeder canal, neat bicycle path, 10-mile hike, bicycle ride. Today, the Canal Corporation, this is a contemporary thing, there are gates because there are no more locks. The old Black River Canal is basically gone. There are parts of it in the valley there, in the gorge, but they had to build gates in order to keep this water here in the, keep it at level in the canal and at their swimming hole over in Boonville and so on. So here are the gates that release the water. So today it still goes downstream to the Mohawk River, and they use it to fill the Delta Reservoir. This is where the water from right here flows south toward the Mohawk River, and it goes down a waterfall into the gorge. And here's where everything is located on a map. Here's Forestport. Here's the feeder canal that I was showing you. That control gates are here. Up here, the river section of the canal. This is where the canal boats were pushed by steamboats, in tows, groups of boats. And of course, this was a conventional part of the canal with mules. And this is an interesting lateral canal. They kept this working until about 1922, years after the Erie Canal was closed, because I suppose they were still hauling a lot of lumber and who knows what else out of the Black River Valley. So they, to design the system up there, they did some crude measurements. An engineer in the early 1830s looked at the flow rate in the Black River. They estimated that they could get about 260 cubic feet per second reliably, and they were wrong. They used 80 of that to make the canal work on the downhill side down to the Black River at Lyons Falls, and then they used 180, and they sent that down to the Erie Canal at Rome. And the reason I'm pointing this out is that this diversion of 180 cubic feet per second was a real bone of contention in the Black River watershed because of all the mills that were located up here at Watertown. This was a very constant area of concentrated of mills for grinding flour, sawmills, weaving. It was very important, and the mill owners back in the 1800s had a lot of political clout. And so when they started to divert water down here at Forestport, this way to Boonville, these people complained mightily, especially when they had low flow periods. And so that led to the state, of course, trying to make the flow into the feeder more reliable, but also to satisfy the mill owners, and there were some here on the Black River too. But they built all flow regulating dams all over the place. They built, these were some of the larger ones, North Lake, South Lake, Woodhull, and they built smaller ones down in here, about 10 or so. And they did that to make the flow more reliable at the feeder canal, the diversion, but also for the mill owners up here. These, I don't know how to go backwards. Oh, here. Yeah, the last three built were here at the Fulton Chain of Lakes, the Old Forge Dam and Reservoir, and Six Lake Reservoir, and Stillwater Reservoir was built in the late 1880s, and they were all just to satisfy the mill owners. They weren't, of course, water doesn't flow down here. It goes, the Black River goes down here and up this way, and the Moose River comes in this way, and the Beaver River comes in this way. So these all were built just for the mill owners. And today, most of those mills have a hydroelectric, small hydroelectric plant there. So how could the early canal engineers have minimized their water problem? Basically, I'll make shorten up the story here. There really was no hope in that in that day. There was no way they were going to figure out what size reservoirs or feeders they needed or how many. They just didn't have the data. They didn't have the techniques. In fact, it took a long time for us engineers and others, hydrologists, to figure out how to get the data. And it wasn't until the 1930s and 40s that we really had the mathematical tools to analyze this data in a way that we could, make engineering sense of it, use of it. They needed data, informations, and methods that they could use to predict, the stream flow in the future, and that became, that was not possible back in the 1800s. So what happened in the late 1800s? We started to get stream flow data from the U.S. Geological Survey. This is the gauging station on the Black River, just downstream from where the feeder is located at Forestport. This is where the pressure is measured of the water that gives you the elevation of the water in the level of water in the stream, and that goes to the U.S. Geological today to their computers. And I'm not going to do it now, but it's logged in real time. The data is collected. You can look at a graph of stream flow. There's about 8,000 of these USGS stations around the country. This is one of the old ones, because I'm sure the mill owners and others, the people that were operating the canal wanted this data, needed this data. And so it's been there a long, long time. The oldest one is about 1890 from down on the Rio Grande River. But then when you go back, I looked at this data from the gauging station at the Geological Survey website. And I looked at this, and you can see how much look at how the flow, this is in a year 2017 to 2018. And there are just, in that 1 year, there were about 25% of the mean daily flow values were less than the 260 needed, that would have been needed in the diversion to the canal. So you can just see in that 1 year, and then when you go to a very dry year, 1960s, the middle 60s were a disaster water-wise for all of the East Coast. And there are even more, particularly there and over here in the late fall. So it's, you look at the historic record that now we have, which they didn't back then, you could see there wasn't enough water in the Black River for both the diversion and, of course, the mill owners that were upset that somebody was diverting their water. So today we have new problems, and we have methods to collect stream flow data. We have methods to model it statistically. We have hydrologic models that we have computer programs that will help us predict how the flow will vary in the future. But now we've run into a new problem. And that problem is called a loss of stationarity. If you want to use the statistical models that help us predict what's going to happen in the future, you have to have data that will hold still. In other words, you calculate statistical parameters for a certain period of years, and then you go later in the record and calculate those same statistical parameters. They should be the same. And of course, they're not. And if you plot all those mean annual flow values that I showed you, here's the one for the 1965. Here's the one for 2018, about 763, I think, and this one's 400 something. You can see that there's a trend upward. And if you do the statistics, you'll see that this slope is statistically significant. It's, significantly greater than zero. So it should be zero if you had stationarity. In other words, if something wasn't changing things. And it seems likely, if you look at the rainfall data, the New York State up here is getting wetter. Since 1950, about 6 or 8 inches on top of the average of 35, 40 that we had then. And that turns out to be just about what this predicts here. So this is about 3% every 10 years in stream flow. And the rainfall increases about 3% every 10 years. So it seems very likely, of course, that the increased precipitation associated with climate change and hydrologists and others have done some really excellent work, showing how this is related to temperature increases and climate change. So this is a problem. The engineering tools that that would be used to design canals and reservoirs and so forth are not working out too well. And this hurts us in several ways. Like also, we're observing these changes in heavy precipitation. More rainfall is falling in the top 1% of the daily events, more precipitation falling. So this is messing things up as far as engineers are concerned, especially when you're an engineer trying to test the ability of a spillway or whatever to pass a storm flow rate. It's getting more difficult to figure out just what sort of standard should you use, how should you calculate the values, and so on. So engineers are wrestling with this problem of stationarity combined with climate change. So it'll be interesting to see how this plays out. So I wanted to finish, I'm just a couple minutes late here. Let me finish quickly. This is the Barge Canal. It's a lot different than the old Erie. There's no mules, no towpath. The tons of cargo went up to hundreds of tons. And of course, the barges are pulled or pushed by tugs, diesels. And the thing is a lot bigger, 150, 200 feet wide, 12, 15 feet deep. The summit section is still problematic. It's over between Oneida Lake and Rome. And the engineers, when they designed, they still didn't have stream flow data, not much. They had, of course, the bad experience of dry periods on the Erie Canal. So when the engineers designed to provide this water, especially for the summit section, it was no holds barred. And they basically designed 3 reservoirs. They built 2, and it's interesting where they might have built the 3rd one if they thought they needed the water. So they built Hinkley Dam and Reservoir on West Canada Creek, over above Utica. This is used for hydropower now, for water supply for the Mohawk Valley water supply system. And to some extent, it's used for flood control. And then they built above Rome, about 6 miles up above Rome, the Delta Dam and Reservoir. And the 3rd one they planned was going to be, it would have been called, I suspect, High Bridge Dam on Limestone Creek. And look, lo and behold, it's on now, this was a little village then called High Bridge. Now this is High Bridge, road into Manlius. And here's the Manlius Library. Here's High Bridge Road. Here's the Cavalry Country Club. Here's Troop K Road. And I just did a rough look at it. I put the dam over here. Looking at the topography, this is probably where the water would have been if the Barge Canal engineers had decided they needed a 3rd reservoir. I said to Bill, the Manlius Library would have lakefront views if this had been built. But anyway, if you go and look at, you think about the US Geological Survey maps that I showed before of the canal down by Fayetteville, in the 1930s, instead of labeling the canal at that location as the Erie Canal, they called it the Barge Canal feeder. So they were, you know, they felt they seriously needed this water from Limestone Creek, Butternut Creek, and so on. So that's the end of the my story. I'll be glad to answer questions.